Welcome to my channel. Today we are going to discuss about the multiple choice question and answer from the part impedance matching in a transmission line or microwave. Okay, so already I posted the 18 videos for the subject antenna and microwave engineering. If you want to learn, I will give the link for those videos in the description box. You can see, or otherwise in my channel antenna and microwave engineering playlist is there, so in that the 18 videos are there. Okay, so thanks for watching my channel and please subscribe my channel for more videos. Okay, so here you see the first question: the major advantage of single stub tuning over other impedance matching technique is dash. So in the impedance matching process, so there are so many methods are there in a impedance matching of transmission line. We can use a stub. In stub, there is a two type of stub is there: single stub matching, double stub matching. And in that single stub, there is a shunt stub and series stub is there. Then one more impedance matching is a quarter wave transformer impedance matching. So these are all the different techniques in order to match the impedance in a transmission line to the load. So the first question: what is the major advantage of single stub tuning over other impedance matching technique? So over other impedance matching technique, what is the advantage of the single stub tuning? Lumped elements are avoided. It can be fabricated as a part of transmission line media. It involves two adjustable parameters, all of the mentioned. So all of the mentioned. So here the lumped elements are avoided. It can be fabricated as a part of transmission line. It involves two adjustable parameters. So all these are the advantage of single stub tuning over other impedance matching technique. Okay. Then the next question: the two adjustable parameters in single stub matching are the distance d from the load to stub position and dash. Okay. So in single stub matching, so there are two adjustable parameters is there. One is given as the distance from the load to stub position. So stub to load, the distance is given. And what is the another one? The susceptance or reactance provided by the stub, length of the stub, the distance of the stub from the generator, none of the mentioned. So the two adjustable parameters, one is the distance d and another one is the susceptance or reactance provided by the stub. Okay, so reactance or susceptance of the matching stub must be known before it is used for matching. So this susceptance and reactance of the stub is a very important key parameter for the impedance matching between the load and source. Okay, so the two adjustable parameters are, one is distance and another one is susceptance or reactance provided by the stub. Okay, then the next one: for series stub matching, the parameter used for matching is dash. So there are two types of stub is there: series stub and shunt stub, depending upon the connection of that particular stub. So in a series stub matching, so which one is the parameter used for matching? Impedance of the transmission line at a point, voltage at a point of the transmission line, admittance at a point of the transmission line, admittance of the load, impedance. So for series stub matching, the impedance of the transmission line at a particular point, it's a parameter. Okay, then the next one: the shunt stub are prepared for dash. So shunt stub, there is a one more stub is there, shunt stub. So these stubs are prepared for strip and microstrip line, coplanar waveguides, circular waveguide, circulator. So the shunt stub is prepared for strip and microstrip line. So in strip and microstrip line, we can use which type of stub? Means the stub for impedance matching is shunt stub. Okay, shunt stub is prepared for strip and microstrip line. Then the next one: in shunt stub matching. In shunt stub matching, the key parameter used for the matching is admittance of the line at a point. Okay, so already we discussed one question in series stub. Okay, so for series stub matching, what is the key parameter for matching is impedance. Impedance of the transmission line at a point. Similarly, for a shunt stub matching, the key parameter used for the matching is admittance. Okay, so you just remember it. If it is a series stub matching, impedance of the transmission line at a particular point is a key parameter. For a shunt stub matching, the key parameter used for matching is admittance of the line at a point. Okay, admittance of the line particular point. Then the next question, for coaxial line and waveguide, dash is more preferred. Open circuited stub, short circuited stub, slotted section, coaxial line cannot be impedance matched. So which one means for coaxial line and waveguide, dash is more preferred means short circuited stub. Okay, that is in so already we discussed one question in strip and microstrip line, which one is preferred means shunt stub. Similarly, for coaxial line and waveguides, the short circuited stub is more preferred. Okay, so these are all the, you just remember it. For coaxial line and waveguide, short circuited stub is more preferred over open circuited stub. Then the next question, the major disadvantage of single stub tuning is. Okay, so the major disadvantage of single stub tuning is it requires a variable length of line between load and stub. It involves two variable parameter, complex calculation, none of the mentioned. So the first one is correct. The major disadvantage of the single stub tuning is it requires a variable length of line between the load and stub. So that is a variable length. In single stub matching requires a variable length line between the stub and load for matching. So which is the major disadvantage of the single stub tuning. Okay. Then the next question. So these are all the questions about the single stub matching. So the next part is double stub matching. So in order to avoid the disadvantage of this single stub matching, we are moving for the next matching. It is a double stub matching. So instead of single stub, here we are using double stub. Okay, stub 1 and stub 2 in between the source and load. It is called as a double stub matching. The major advantage of double stub tuning is dash. So what is the advantage? In order to overcome the disadvantage of this single stub matching, we are moving for this double stub matching. Okay. So what is the advantage of that double stub matching is it uses two tuning stub in fixed position. Okay, in single stub matching, the variable length line, okay, we are using that requires a variable length of line between the load and stub. Okay, that is a major disadvantage. In order to overcome the disadvantage of the single stub tuning, we are using the double stub tuning. So here this double stub tuning requires two tuning stubs in fixed position. Okay, so that the length between the first stub and the load is not variable. So that is the advantage. It uses two tuning stub in fixed position. So the position is not changed. Okay, so that's the advantage of the double stub tuning. The next one, in a double stub tuner circuit, the load is of dash length from the first stub. So the load in double stub tuning, the load is of dash length from the first stub. So the load is of fixed length, arbitrary length, depends on the load impedance to be matched, depends on the characteristics impedance of the transmission line. So the load is of arbitrary length. Okay, the position of the first stub in a double stub tuner is variable from the load end. Okay, so one stub is the position of the distance between the first stub to the load is variable, but the distance between the two stubs is always fixed depending upon the impedances matched. So the load is of arbitrary length from the first stub. Then the next question, the double stub tuners or fabricated in coaxial line or connected in shunt with the main coaxial line. So this is true or false? It's a true. Okay. So most of the transmission lines used in our practical application use the coaxial cable. Okay. So for which, in order to provide the impedance matching, the double stub tuners are maximum suitable method. So for coaxial cable, the double stub tuners are maximum used in order to provide the impedance matching. Then the next question, all load impedances can be matched to a transmission line using double stub matching. All load impedances can be matched to a transmission line using double stub matching. True. Okay. So any load impedance can be matched to a transmission line using this double stub matching. Yes, it's a true only. Then the stub spacing that are near 0 and lambda by 2 lead to more frequency sensitive matching network. It's a true or false? It's a true. Okay. So the stub spacing, the distance between the two stub is nearly 0 to lambda by 2. It lead to more frequency sensitive matching networks. It's a true only. Then the next one, the standard stub spacing usually used is dash 0, lambda by 2, lambda by 4, lambda by 8, lambda by 8, 3, lambda by 8, none of the mentioned. Okay, so the standard while the stub spacing of 0 lambda by 2 lead to frequency sensitive matching circuit. Okay, so the optimum value of the spacing is chosen, taken into consideration for the various design constraint. So the optimum spacing used is lambda by 8, 3 lambda by 8. Okay, so the standard subspacing is used as lambda by 8, 3 lambda by 8. So if you are choosing 0 lambda by 2 means it provides the frequency sensitive matching circuit. Then the next one, if the normalized admittance at a point on the transmission line to be matched is 1 plus j 1.47, then the normalized susceptance of the stub used for shunt stub matching is dash. Okay, so for the transmission line, normalized admittance is given 1 plus j 1.47. Then what is the normalized susceptance of the stub for shunt stub matching? Okay, so when the shunt stubs are used for impedance matching between a load and a transmission line, the susceptance of the shunt stub must be negative of the line susceptance. Okay, so here you see 1 plus j 1.47. So this 1.47. So the susceptance is always negative of the line susceptance. So here the susceptance is 1.47. So the susceptance of the shunt stub matching is minus 1.47. Okay, so in this 1 plus j part, this imaginary part, it is called as a susceptance. So for the susceptance value, you have to take the negative value. So minus 1.47 ohm is the answer. The next one, in series stub matching, if the normalized impedance at a point is 1.33 means, then what is the reactance of the series stub used for matching? So similar to the previous problem, that is for the shunt stub matching. Okay, so this is for shunt stub matching. For shunt stub matching, admittance is given. The question is normalized susceptance of the stub. So here for series stub matching, impedance, normalized impedance is given 1.33. Then what is the reactance of the particular series stub? Okay, so the reactance of the series stub is also the negative of the reactance of the line. So what is the reactance of the transmission line? Plus 1.33. So the reactance of the series stub is minus 1.33. So you just take the negative part of the reactance given. So minus 1.33 ohms is the answer in order to provide the impedance matching. So these are all the questions about the single stub and double stub matching. So the next impedance matching device is quarter wave transformer. The third impedance matching in a transmission line is quarter wave transformer. A quarter wave transformer is useful for matching any load impedance to a transmission line. The statement is true or false? False. So the quarter wave transformer is useful for matching any load impedance to a transmission line. The statement is false. The quarter wave transformer or a simple circuit that can be used to match the real load impedance to a transmission line. If the load impedance is only real value, that is resistance, means at the time only we can use this quarter wave transformer for impedance matching. So this one is a false. Okay. If it is a complex, if the transmission line is having complex load impedance, the quarter wave transformer cannot be used for to match. So that's why the statement is false. Okay. The major advantage of the quarter wave transformer is it gives proper matching, it gives high gain, broader bandwidth, none of the mentioned. So the major advantage of the quarter wave transformer is that it provides the broader bandwidth. Okay, broader bandwidth, that is the advantage. Then the next one, if the narrow band impedance matches are required, then more multi-section transformers must be used. So the statement is either true or false. It's a false. If narrow band impedance matches are required, then single section of quarter wave transformer is used. So for a narrow band impedance match, we may use only single section quarter wave transformer. For wide band impedance matching, we can use multi-section. So here for narrow band impedance matching, more multi-section transformers used. It's a false statement. For narrow band impedance match, single section quarter wave transformer is used. For wide band impedance match, multi-section transformer is used. Then the next one, the major drawback of a quarter wave transformer, that is that it cannot match complex load to a transmission line. It cannot be overcome. Already you know the quarter wave transformer, it can match only the real load of transmission line. But then it cannot be matched to a complex load to a transmission line, but in it cannot be overcome. This is the false. That is the major drawback of quarter wave transformer, that it cannot match complex load to a transmission line, but it can be overcome by transforming the complex load impedance to real load impedance. So we can transform the complex load impedance to real load impedance. After transforming, we can use this quarter wave transformer for impedance match. So that's why this drawback we can eliminate, we can overcome. Okay, so that's why the statement is false. Usually the quarter wave transformer, it cannot match the complex load of transmission line, but this drawback we can overcome by transforming the complex load impedance to real load impedance. Okay, the next one, the complex load impedance can be converted to real load impedance by dash. Okay, how to convert the complex load impedance to real load impedance in this quarter wave transformer? Scaling down the load impedance, introducing an appropriate length of transmission line between the load and quarter wave transformer, changing the operating wavelength, none of the mentioned. So the complex load impedance can be converted into real load impedance by introducing the appropriate length of transmission line between the load and quarter wave transformer. That is the correct thing. The next one, converting complex load into real load for impedance matching has no effect on the bandwidth of the match. That is here in quarter wave transformer, if the load is complex, means we can convert into real load. Okay, so that conversion it has no effect on the bandwidth of the match. This is false. Okay. Adding the length of line to transmission line between the load and quarter wave transformer, it alters the frequency dependence of the load. Okay, thus alters the bandwidth of the match. So that's why the bandwidth is also changing. If you are converting complex load to real load for impedance matching, it will affect the bandwidth. So the statement is false. The next one, in a single section quarter wave transformer is used for impedance matching at some frequency, then the length of the matching line is dash. Okay, in a single section quarter wave transformer is used for impedance matching at some frequency, then the length of the matching line is different at a different frequency, is constant, is lambda by 2 for other frequency, none of the mention. It is different. The length is different for different frequency. Different for different frequency. The next one, quarter wave transformer cannot be used for non-TEM line for impedance matching. It's a true. So quarter wave transformer, it cannot be used for non-TEM line for impedance matching. It's a true only. Then the reactance associated with the transmission line due to discontinuities, it have to be matched. Okay, the reactance associated with the transmission line due to discontinuity have to be matched. The next one, if a load of 10 ohm has to be matched to a transmission line of characteristics impedance 50 ohms, then the characteristics impedance of the matching line of transmission line is dash. So for one transmission line, the load is 10 ohms. The transmission line, the characteristics impedance is that not is 50. Then what is the characteristics impedance of the matching section? Okay, so you see the characteristics impedance of the matching section of transmission line is given by the Z is equal to square root of Z naught into ZL. So here what is Z naught? Characteristics impedance of transmission line. What is the answer? 50. So square root of 50 into load 10. So square root of 50 into 10. So square root of 500. So square root of 500. The answer is 22.36. So the characteristics of this quarter wave transformer, this matching section means quarter wave transformer. So the characteristics of quarter wave transformer, if load is 10 ohm and the characteristics impedance of the transmission line 50 means, so the answer is Z is equal to square root of Z naught into ZL. So this is 22.36 ohms. Okay. So these are all the some of the questions about the impedance matching in a microwave communication or a transmission line in between the source and load. So here we may use single stub matching, double stub matching and quarter wave transformer. Okay. So thanks for watching my channel and please subscribe my channel for more videos. If you want to learn the remaining videos, I will give the link for those videos in the description box or in a antenna and microwave engineering playlist. So all videos are available so you can see. Okay, so thank you. We will meet in the next video. So thank you.